going to take you through three different laws, the same three laws as you read about in the reading assignment. We're going to look at Boyle's law, and Charles' law, and then Avogadro's law. And we're going to put those together. I think I mentioned yesterday that the ideal gas law, PV equals nRT, is the backbone of this whole chapter. Everything kind of goes back to PV equals nRT. And I think you're going to see that as we go through. Like in the case of Boyle's law. Last year in Chem 1, you would have learned Boyle's law as a relationship between two PV expressions. It's not the way Boyle's law is going to look in here. Because there's a different objective this year with the gas laws than there was last year. You're going to feel for that very quickly. So when I was making up this slide, I grabbed this picture off the internet just in the last couple of days. And I thought, well, that looks good. That it describes Boyle's law just fine. But then today, this morning, when I was rehearsing what I was going to do today, I looked back at this and said, oh, that's a bad picture. Can anybody look at that picture and notice anything that does not look correct? There's two things that I don't like about the picture. I didn't look carefully the first time. Shaitanya?
This is the arrow.
What about?
For being pointed on the second picture.
Over here, the second picture? Which one? That
No,
that arrow?
the top of it.
That one?
Yeah.
What don't you like about it?
It's like it bounced off something that's not.
We don't know what. Yes, that's what I'm thinking. There's a number of these arrows, like that one. That particle kind of bounces off of the top part and then goes over there, and then suddenly just changes direction and goes back that way. Gas particles don't do that. We assume that they just go in a straight line until they bounce off the container, or possibly one of the other particles, but that's not likely because they're spread so far apart from each other. And this one too, look at this particle. I love this particle. It goes in, and it's going this way, and then it hits there, but then it bounces back the same way that it can. Come on! Now, I shouldn't make fun of this person, whoever made this picture, because I didn't make the picture, so I borrowed it from them. So maybe I ought to keep my big mouth shut, but it's good for a smile to me. Another thing that is, I think, wrong, misinterpreted, or misportrayed in the picture is something else. Tell me about the arrows. It's fine, you know, that they're bouncing off, the arrows are changing direction. What else about the arrows? Anybody want to take a stab at this one? Notice the arrows in this one, and then the arrows in this. Does it look like these arrows are longer? They're showing all the bouncing around that the particles are doing. But the fact that they're longer means what about their motion? Probably that they're going faster. Yeah. And when we're dealing with Boyle's law, Boyle is assumed that it's changing the volume and the pressure, but keeping the temperature constant. And we should not have longer arrows, even if they're jointed arrows. They shouldn't be longer than what they were over there, because that implies that they're going faster. Yes, they're bouncing into the walls of the container more frequently, but the speed of the particles themselves is the same. Okay, so now having beat up on that artist, let's take a look at Boyle's law. Boyle's law deals with the relationship between pressure and volume. Now going back to this, if I could use this as an authentic example of Boyle's law, we have a certain pressure and volume here, but when the volume gets squashed down, the pressure is going up. The particles have a smaller, more confined space to move around in, so they're bouncing off the walls of the container more frequently, increasing the pressure. So I know that you just did this, this reading assignment. How would you categorize the relationship between volume and pressure? It's an inverse relationship. When the volume goes down, the pressure is going up. So that means an inverse relationship would look like this. We would have, when the pressure is low, the volume is high. And when the pressure is high, the volume is low. And that relationship is graphed. If we were to take several data points, it would be a curved graph like that. Now, you did the reading so that you know what happens when we invert one of the variables. If I just take volume versus pressure, I get a curve. But if I measure volume versus the inverse of pressure, you remember what that gives? It does. It gives a straight line. So you get this kind of a curve. And if we just give the slope a name, I'm going to call it K. I know the book called the slope K too. K also. So that when we express the equation for this line, the equation for this curve is not so simple. The straight line is always simpler. Then the inverse relationship would look like this. The volume, which is the y, equals slope, which is K, times this x, which would be the inverse of P, inverse of pressure. So right there, that is an expression of Boyle's law. That K value, we don't really care what numerically it is. It would depend on the non-changing variables, like the temperature would affect what the K value is. As long as you're not changing the temperature while you're measuring the volume and pressure, you'll get a certain straight line. Oh, and there he is. I don't want to have you miss him. That's Robert Boyle, a painting of him from the 1600s. Amazes me that these discoveries were made this long ago. I think I mentioned that yesterday about Torricelli, the mid-1600s. Man, there was so little information back then from these guys to come up with those relationships. It was awesome. Even how would you measure pressure back in the 1600s? It's cool. Okay. The next big discovery was by Jacques Charles. And this is about 100 years later, in the late 1700s. Charles, of course, was French with a name like Jacques. What else could he be? But notice his hobby. I don't think that was his vocation, being a hot air balloonist, but he was a hot air balloon guy, pilot. And so it's appropriate that he would come up with a relationship between the temperature of the gas and its volume. He found that if you keep the pressure constant, which the pressure inside of a hot air balloon is fairly constant, you heat that gas up, it gets bigger. So, and this is the same picture that I had in the reading quiz. And I really like this picture. I think they did everything right in this picture. We see, and I even counted because I'm a nerd, 12 particles in there, and it's still 12 particles in there, so we're not escaping particles or anything. And you see the little bitty flame there, keeping that at a certain volume. The flame goes up, whoop, the volume of the gas goes up, particles are spread more far apart. We assume that the pressure stays the same when we have a Charles law change. So the pressure is the same, and that pressure being the same would have to cause the piston to expand. All right. Well, how would we characterize this graph here between volume and temperature? It's a direct relationship, so as the temperature is going up, the volume is going up, and it does so with a linear relationship in this case. So we would be able to measure the slope of that line, maybe increase the temperature some, see what the new volume is. Increase the temperature a little more, see what the new volume is. We get a straight line. I'm going to call the slope in this one K as well. I think the Zumwalls were more careful to not use the same letter to symbolize the slope. But what the heck, you're going to see that it doesn't really matter. We don't ever know what the value of K is because K can change. There's Jacques Charles. And so we can see, just giving the equation of the line, volume equals K times T. This right here would be expressing Charles' law. Now I know that this is not the Charles law that you saw last year. You saw V1 over T1 equals V2 over T2 last year. But it kind of starts with this. Now our next big discovery was Avogadro's law. Amedeo Avogadro. You'll recognize this guy. Where have you seen him before? This is me on Schoology. I use Avogadro's picture for me, my little avatar. And Avogadro, he came up, even though he looks like he's in pretty rough shape, I wonder if the artist that drew his picture was mad at him. But anyway, unfortunately for Avogadro, that's how he's immortalized, is with that picture. But in spite of the way he looks, man, was he smart. He came up with this marvelous relationship, recognizing that when you have two gases that have the same volume and temperature, like these two balloons, or there's three balloons, 1, 2, 3. All of them, let's assume they have the same volume. They're all in the same room, so they have the same temperature. Those equal volume balloons, even if they're different gases, will have the same number of particles in them. So same volume means the same number of particles. That's Avogadro's law. And so that leaves us with this relationship. Volume and number of moles of gas is directly related. If you have more moles of gas put into your container, you're going to have a higher volume. So this one is very similar to the Charles law relationship, because it's a direct relationship. Putting these three together. Now I want you to notice something, that Avogadro's law, we solved it for volume. Volume equals some expression with the other variable. With Charles' law, it was something that was solved for volume. And then with Boyle's law, we were solving for volume. So in every case, it's volume equals something. If we put those three together, we're going to get a relationship that looks like this. Volume equals K times 1 over P, that's Boyle. Volume also equals K times T, that was Charles, and K equals K times N, that was Avogadro. So all these things are equal to V. That means if we put all three of these terms together, that means that volume equals some constant times NT over P. And if we just rearrange this K now, that it relates all four of the gas law variables, and now the K is actually going to matter. We're going to give K a different name. That's what I'm saying down here. We're going to call that K R. So that for any gas, as long as it's acting like an ideal gas, obeying the four guidelines, I guess, of the kinetic molecular theory, for any gas, you'll get a straight line when you plot the pressure times volume versus the moles times temperature. It'll give you a straight line every time, as long as it's ideal, with the slope of that line equal to R. Now, I had somebody ask me one of the earlier hours, hey, it looks like you have a 45-degree angle. Doesn't that mean that R equals 1? And that's absolutely not true, because the N times T is going to be some value here. The graduations on this axis are not the same as on that axis. If they were, then the slope would be 1 if it were a 45-degree angle. But it doesn't even necessarily have to be a 45-degree angle. It depends on what the units are of the moles, temperature, pressure, and volume. But the R value is a constant. And you learned about R last year in Chem 1. You remember any of the values of R? We have 3 values. What do you have? John, do you remember one? Okay, that's okay. Anybody remember R? Do you feel it?
It was like 2.2.
No, it wasn't 2 point something. Justin.
101.32.
Well, actually, that one is standard pressure. That's standard pressure in kilopascals. The value of R, though, do you remember?